according to our best model. The universe should be expanding more slowly than it appears to be today. We can look back to a time when the cosmos was only 380,000 years old. We can also measure the universe surrounding us now. Yet when scientists try to connect those two moments, they do not arrive at the same expansion rate. The early universe gives us a value close to 67. The nearby universe gives us something closer to 73. One is a prediction based on the standard cosmological model. The other comes from direct observations of stars and exploding supernovae. Both methods are remarkably precise, and that is exactly what makes the disagreement so difficult to ignore. Then James Webb ruled out one of the strongest explanations for why the numbers refuse to match. For decades, cosmologists believed they understood the broad outline of the universe's history. It began in an unimaginably hot and dense state, then expanded and cooled. Matter gathered under gravity. The first stars ignited, galaxies took shape, and billions of years later, the expansion of space began accelerating, an effect scientists attribute to dark energy. Evidence of that early universe still surrounds us. The cosmic microwave background is the oldest light we can observe, released when the universe cooled enough to become transparent. It preserves an extraordinarily detailed picture of the cosmos as it existed near the beginning. By measuring that light, scientists can reconstruct the early conditions of the universe, enter them into the standard model, and calculate forward across almost 14 billion years. If the measurements are right, and the model contains every important ingredient, the result should resemble the universe we see today. It is like knowing where a ship began its journey, how fast it traveled, and every current it encountered along the way. Its final position should not be a mystery, but the real universe arrived somewhere else. The first number comes from the European Space Agency's Planck mission, which mapped the afterglow of the Big Bang in extraordinary detail. When scientists interpret Planck's observations through the standard cosmological model, they arrive at a present-day expansion rate of roughly 67.4 kilometers per second per megaparsec. The second number is built much closer to home. Adam Rees and the SHOES team begin with pulsating stars known as Cepheid variables. They use those stars to calibrate Type 1a supernovae, creating a distance ladder that stretches outward through the nearby universe. Their result remains close to 73. Same universe. Two independent routes. Two different answers. Planck begins with the early universe and uses the standard model to predict the expansion rate today. SHOES measures the late universe, using calibrated stars and supernovae. That distinction does not make the disagreement disappear. It is the disagreement. At first, this looked like the kind of problem that better observations would eventually solve. As the instruments improved and the uncertainties became smaller, the two values were expected to move toward one another. They did not. Instead, the gap became harder to dismiss. There was still one plausible explanation. Hubble's measurements of Cepheid stars might have been distorted by the crowded regions surrounding them. James Webb could finally test that possibility. Cepheid variables brighten and fade in a predictable rhythm. That rhythm tells astronomers how luminous the star truly is. Once they know its real luminosity, they can compare it with how faint the star appears from Earth and calculate how far away it must be. The method is powerful, but it has a weakness. Cepheids often sit in densely packed regions of their galaxies. Through Hubble's cameras, the light from neighboring stars can blur together with the Cepheid itself. That makes the star appear brighter and therefore closer than it really is. If that effect became stronger with distance, it could push the locally measured expansion rate upward. The possibility was reassuring because it offered a conventional explanation. The universe was not behaving strangely. Hubble was simply struggling to separate one star from another. Webb was designed to see those crowded regions more clearly. Its infrared instruments can distinguish neighboring stars with greater precision, while also reducing the effects of dust. Rees and his colleagues used Webb to remeasure more than 1,000 Cepheids in galaxies that had already been observed with Hubble. The expectation was straightforward. If crowding had distorted the older measurements, Webb should produce different distances. That is not what happened. The stars became clearer. The scatter in the measurements became smaller. The distances remained almost unchanged. The telescope had changed. The result had not. Webb did not eliminate every possible source of error. What it did was strongly reject the idea that previously unrecognized Cepheid crowding, increasing with distance, had created the entire tension. It did not create the mystery. It removed one of the strongest ways out. That leaves a more unsettling possibility. The prediction from the early universe and the measurements made nearby may both be broadly reliable, while something is still missing from the physics connecting them. One possible missing ingredient is early dark energy. Unlike the dark energy believed to dominate the universe today, this would have been temporary. It may have influenced expansion in the young cosmos, and then faded before the first stars began to shine. Imagine giving a train a small, unexpected push near the beginning of a very long journey. At first, the difference would be almost impossible to notice, but after traveling for billions of years, the train would arrive far from the position shown on the original timetable. Early dark energy could have changed the conditions of the young universe just enough to bring the predicted expansion rate closer to the one measured today. The problem is that no one has detected it directly. Different analyses also disagree about how much early dark energy the existing evidence would allow. For now, it remains a candidate, not an answer. And expansion is not the only area where the early universe has surprised us. Some of the first galaxies observed by Webb initially appeared far too massive for the time in which they existed. Later analysis showed that rapidly growing black holes had inflated the brightness of several candidates, making their galaxies appear heavier than they actually were. That weakened the most dramatic claims. It did not remove the puzzle entirely. Astronomers still observe more massive early galaxies than some models predict. Stars may simply have formed more efficiently in the dense conditions of the young universe. That would require changes to our models of galaxy growth, rather than an entirely new cosmology. These galaxies do not explain the Hubble tension, but they reveal something important. The early universe repeatedly produced outcomes that our simplest models did not anticipate. The problem may not lie entirely at the beginning. It may not lie entirely in the present. It may lie in the way we connect them. For Adam Rees and the SHOES team, one of Webb's most important results was not a spectacular image of a distant galaxy. It was a comparison. On one side were the Cepheid distances measured with Hubble. On the other were sharper measurements of the same kind of stars made with Webb. If crowding had significantly distorted Hubble's observations, the two sets of measurements should have separated. Instead, they landed almost on top of one another. The telescope had changed. The result had not. That comparison carried the weight of decades spent searching for an explanation that might bring the two expansion rates back into agreement. Perhaps better cameras would reveal blended stars. Perhaps a larger collection of supernovae would expose a hidden bias. Perhaps independent distance markers would show that Cepheids were less reliable than astronomers believed. Each improvement offered another chance to test the result, yet the central discrepancy remained. That is not the kind of discovery people usually imagine when they think about science. We picture a sudden answer, a new object, a dramatic image, a final equation written on a board. But discovery can also be slower and more uncomfortable. Sometimes progress means realizing that repeated attempts to explain a contradiction within the existing framework have not been enough. The standard cosmological model is not collapsing. It still describes the cosmic microwave background and the large-scale structure of the universe with extraordinary precision. But Rees and other cosmologists are now working at its boundary. They are using ancient light, distant explosions, and mirrors built on Earth to reconstruct a history no human being could ever witness directly. And the more precisely they measure that history, the more difficult the missing connection becomes to ignore. A hidden systematic error may still exist, but if it does, Webb has made it more difficult to find. An independent analysis led by Wendy Friedman combined several methods of measuring stellar distances and obtained a value close to 70 between the Planck and SHOES results. The individual methods did not agree perfectly with one another, which means the local distance scale is still being tested. That uncertainty matters. It leaves open the possibility that the tension will eventually be resolved without changing the fundamental laws of cosmology. But it also means scientists need entirely new ways of tracing how the universe evolved. Euclid is already mapping the growth of cosmic structure across billions of years. NASA's Nancy Grace Roman Space Telescope will provide a much wider view of dark energy and the large-scale universe. Together with new distance ladder measurements, these observations may reveal whether the disagreement changes with cosmic age. Did an unknown form of energy briefly alter the young universe? Is another systematic error still hiding inside our measurements? Or does the standard model connect the beginning to the present with one assumption too many? Cosmology has faced contradictions before. And sometimes the solution was not a better measurement of something familiar. It was the discovery of something that had been missing all along. We can see the universe shortly after it became transparent. We can study the world it eventually became. But almost everything between those moments has been reconstructed from ancient light, distant motion, and mathematics. We are trying to recover the history of existence from fragments that traveled billions of years to reach us. The beginning left a picture. The present left another. What we may still be missing is the journey between them.